All right, look at us, chapter 13. All right, so today we're going to learn specifically about rotational kinetic energy, and there will be a little bit more of a discussion about rotational energy, but definitely the focus is on this guy, rotational kinetic energy. All right, so here we go. All right, oh my gosh, can you see it? You can. Oh man. All right, sorry. Okay, so what I would like you to do is I would like you to imagine, let's do this. Oh, there we go. Imagine this meter stick now. Here you can see this meter stick, check it out, meter stick. So imagine that meter stick sliding along a frictionless surface at 5 meters a second, right? So it's just sliding through space like this, right? Okay. So if we wanted to do that, we can definitely calculate the kinetic energy, right? What would we do? We would just go, okay, well, the kinetic energy is 1/2 times the mass of the meter stick times its velocity, 5 meters a second. Holy cow, don't forget to square it, multiply it out, and if you do this, it gives you 0.75 joules. All right? So, cool. Now, what would happen if, instead, what if the meter stick was rotating around its center? What if the meter stick was rotating around its center? So now we've got this. Instead of it moving, we're going to have the meter stick rotating. So take a look at this. So what's happening is the 50 centimeter mark isn't moving at all, right? But what happens is the other points on the meter stick definitely have different velocities, right? So my 50 centimeter mark is here-ish, right? But the idea is the farther you go out, because remember, velocity is angular velocity times radius. So as your radius gets bigger, your velocity gets bigger, right? So this point out here has a bigger radius and therefore a bigger velocity. This particle out here has a bigger radius and therefore a bigger velocity. And these particles all the way at the end have a really big radius and therefore a really big velocity, right? Okay, and so the idea is different particles on the meter stick are going to have different velocities, right? So even if two particles have the same mass, they're going to have different velocities and therefore different kinetic energies, right? Okay, so what if we did that? What if we rotated the meter stick around its center? So this time I'm giving you an angular frequency, right? Or an angular velocity, sorry. Okay, so our angular velocity is 10 radians per second. All right, so then what's going to happen is different particles of the meter stick are going to have different velocities, right? So if we went through and added up all of the particles along the meter stick, we'd have mass of particle 1 times the velocity of particle number 1, right? And repeated for object 2, object 3, until we've added up all of the particles in the object, right? Okay? But so what we can do now is what we're going to do is we're going to take each of these velocities and replace them with an angular velocity, okay? So the velocity of particle number I is equal to the angular velocity of the meter stick times the radius of particle I, right? So now my kinetic energy is 1/2 mv squared, and v is just omega r, right? So notice the omega is the angular frequency of the whole meter stick, so I can pull that out, right? Because that's going to affect each term equally. And so look what I get. I've now got 1/2 times a whole bunch of mr squareds times omega, right? Okay? But notice this, the mass of each individual particle times its radius squared, that's a property of the object, right? Because the different particles of the meter stick have their own certain positions, right? Okay? So this sum is our rotational inertia. So remember, when we learned about rotational inertia, we learned that the rotational inertia of a particle is mr squared. This is why. Because here's our mr squared. Okay? And so now, if you want to find the kinetic energy of that meter stick, it's 1/2 I times omega squared, where I is the total rotational inertia of the whole stick. All right? Now, to be clear, I usually use the notation RKE as in rotational kinetic energy to make a distinction between that and what we usually just call kinetic energy. All right? And I'm going to try to continue when I solve problems. I'll use TKE to represent the combined result of rotational and regular kinetic energy. Okay. Occasionally, well, yeah. Okay. Cool. So that is that. All right, so once you've got the rotational inertia, calculating that, the rotational kinetic energy is easy. But how do we find I? Well, we have already learned about that, right? We learned about that last chapter, right? Okay, so once again, you've got all these different rotational kinetic energies for different shapes. This is all review. I'm not going to go through it again because you've already learned all of this. Here's your rotational inertia for a particle. All right. So if our meter stick is in fact rotating about its center at 10 radians per second, then we ought to be able to find the rotational kinetic energy, right? So let's write out what we know. So here we know the mass of the meter stick was 0.06 kilograms. We know that it is a rod rotating about the center, right? And so I, for a rod rotating about the center, is m, no it isn't, sorry, it's 1/3 mr squared, where r is this distance, right? So for us, r is half a meter, right? Okay. So we can calculate our I. The rotational inertia of our meter stick is 1/3 times the mass times r. Don't forget to square it. And when you do that, it gives you a number that I've written on this piece of paper right here. It gives you 0.005. Notice the units are kilogram meters squared. All right, so that is the rotational inertia of the meter stick. And so now I can find the rotational kinetic energy. It is 1/2 times I times omega squared, which is 1/2 times I times omega, which was what, 10 radians per second? Don't forget to square it. And so if you figure this out, it gives you 0.25 joules, which is half as much kinetic energy as the meter stick had when it was just moving linearly, which doesn't really mean anything, but it is. That won't always be the case, so please don't make that generalization. I shouldn't have even said that. Cool, so that's that. All right, so to be clear, what this was an object that was just rotating, right? So we had our meter stick back here, right? And that meter stick was just, no, it's not going to let me do it again, darn it. Oh yeah, well, here we go. So our meter stick was just rotating, right? So all of the motion of the meter stick was linear, right? Now, eventually we'll get to rolling, which is a combination of spinning and, and moving. It's not going to let me do it. But what happens if you've got a particle that's like moving in a circle, all right? So let's do this. So what if I've got a 10 kilogram object, so maybe it's a giant bowling ball or something, moving in a circle that has a radius of 4 meters at a velocity of 5 meters a second. All right, so here's my bowling ball. All right, it's going around in a great big circle here. The radius is 4 meters. Our velocity is 5 meters a second, and our mass is 10 kilograms, right? All right, so the question is, do I consider this as kinetic energy or as rotational kinetic energy? And the answer is, it turns out that it doesn't matter, okay? So let's do this. Let's start by finding the kinetic energy. All right, so kinetic energy, remember, kinetic energy is not a vector, so it's just 1/2 mass times the speed squared, the velocity squared. Here's your speed, here's your velocity, right? So half of the mass times the velocity, times the velocity squared. So that gives you 125 joules. Cool. All right. Now, what if, I don't know why you would do this. Certainly this has linear velocity, and therefore it has linear kinetic energy. But suppose I wanted to calculate this in terms of rotational kinetic energy, which honestly would be a little bit weird because technically the point isn't rotating, right? It's revolving, right? But you could, if you wanted to, you could think of this as a thing that's revolving, or rotating, I guess, around some central point, right? Okay, so if I do that, then let's see what happens here. So first of all, I got to clear up some board space here. So we'll do one of these again. Oops. Oh my gosh, it's not going to do it. Stupid board. All right, so just remember, we got 125 joules. I'll make a little note off to the side. The kinetic energy that we calculated was 125 joules. All right, let's find the rotational kinetic energy. So rotational kinetic energy is 1/2 times I times omega squared. All right, well, let's see. I for a point particle is just mr squared, right? And the angular velocity is v over r, right? So let's see, so what are we going to get? So the rotational kinetic energy is 1/2 times I times omega squared. And look what happens. Here I've got an r squared, and here I've got an r squared, and I'm left with 1/2 mv squared. It's going to give me the exact same answer, right? Okay, so if you have sort of a point particle traveling in a circular path, you consider its energy of motion in terms of either kinetic energy or rotational kinetic energy, but not both. Please don't count it, okay? You consider it as either kinetic energy or rotational kinetic energy, all right? The only time that you need to double count is if you have an object rolling. So if I've got an object that's rolling, then it's got rotational kinetic energy simply because it's spinning, right? If you look at this, so like if you look at this thing, it is, while it's rolling, it's spinning, right? But it's also, in addition to that, moving through space, right? So we have both rotational and kinetic energy. And that is, if I remember right, the focus of the next video. There you go. How was that? Today's video, nice and short, right? Cool.